Let's look at some practice buffer problems. So make sure that you have your calculator handy and your Appendix D. All right, so we want to calculate the pH of a buffer that has 0.12 molar in lactic acid. So this is our HX concentration and 0.11 molar in sodium lactate. So again, this is our salt that 100% dissociates. So we know that this is our lactate, or the X minus concentration. Great, so let's find the Ka of lactic acid. So we're going to look up lactic acid for 1.4 times 10 to the negative 4. So we've got our Ka, 1.4 times 10 to the negative 4. So let's plug this right into the Henderson-Hasselbach equation. Our pH is equal to the negative log of our Ka, 1.4 times 10 to the negative 4, plus the log of our base, which is 0.11, over the concentration of our acid, 0.12. So we just need to do some calculator work here. The negative log of 1.4 times 10 to the negative 4 plus the log of 0.11 divided by, divided by 0.12. We should get a pH of 3.82 units. Now it makes sense if we've got lactic acid in there. All right, let's look at this next one. Calculate the pH of a buffer formed by mixing. Okay, so we're given a volume and a concentration of that lactic acid with a volume and a concentration of the conjugate base. So since we're mixing two different volumes, we need to do our M1V1 equals M2V2 to figure out what the concentration will be when we mix these two volumes together. So let's look at that first. We'll look at the lactic acid. We'll do M1V1 equals M2V2. So the molarity first was 0.13. Volume was 85 milliliters. We don't know what the new concentration is after we mix it, so we're going to say M2, but V2, volume, after I mix them, is 85 plus 95, which, let's just do some, make sure I don't mess it up, 85 plus 95, 180 milliliters. So we just need to divide both sides by 180 milliliters to get our molarity for our lactic acid. So 0.13 times 85 divided by 180. So our new molarity is, let's go to 2 sig figs, 0.061. Well, you know what? I'm going to go one more since we'll round at the very end. 0.0614. Okay. So there's our lactic acid. Now let's do it for our sodium lactate. All right, so our M1 is 0.15. V1 is 95 milliliters equals, I got to find my concentration, and then volume is the same volume. One is 180. All right, so divide both sides by 180. So M2 is 0.15 times 95 divided by 180, 0.0792. Okay, there's our concentrations. Now we can plug we've got our acid concentration, we've got our lactate concentration, which is that conjugate base, Now we can plug that into the Henderson-Hasselbach and find the pH. So I'm going to use a different color here. We've got pH is equal to the negative log of the Ka of lactic acid, which we just found up here, are 1.4 times 10 to the negative 4, plus the log of our base, which we said is 0.0792 over our acid, 0.0614. And let's plug this in and see what we get. So negative log of 1.4 times 10 to the negative 4 plus the log of 0.0792 divided by 0.0614. Should get 3.96 pH units. Notice that our pH rose a little bit. If we look, let's see, my acid concentration was definitely smaller. It was about half of the concentration, went from 0.12 to 0.06. And my base was at 0.11 there, and my base went down just a little bit, but my acid concentration was in half. So, all right, let's look at number 3. The pH of this buffer, so we have 5 grams of ammonia and 20 grams of ammonium chloride added to enough water to form 2.5 liters. All right, so hopefully bells are going off and you're like, oh, we can't do anything with grams. Grams, we have to get to moles. So let's do that. We have 5 grams of ammonia, which is NH3. And we should be able to recognize that ammonia is my base. All right, so let's do grams to moles. If I add up nitrogen and 3 hydrogens, I should get 17 grams of NH3 and 1 mole of NH3. So 5 divided by 17, 0.2941. That's moles. And let's go even further. We want moles per liter to get molarity for our base. So let's divide that by 2.5 liters. So divided by 2.5, and we'll get 0.118. Okay, so we have concentration for my ammonia. Let's do the same thing with our 20 grams of ammonium chloride. NH4Cl, ammonium chloride. So this is going to be my conjugate acid, right? Our ammonium chloride is just going to be a spectator ion. So our conjugate acid, with that being my base. So let's figure out molar mass of ammonia, ammonium chloride. 1 nitrogen, 4 H's, and 1 chlorine should be, 53.5 grams NH4Cl and 1 mole of NH4Cl. So 20 divided by 53.5. And we're going to do the same thing. We're going to take our answer at 0.3738 moles, and we're going to divide that by 2.5 liters. So we can get molarity of that. 0.14, well, we're going to say 0.150. All right. So now we need to do some plugging into our Henderson-Hasselbach equation. To find the pH, we need the negative log of the pKa, or I'm sorry, I'm going one step too far. pH is equal to the pKa plus the log of our base over our acid. So we know that we were able to do this by the negative log of the Ka, but we don't have the Ka, do we? Because this is NH3, ammonia is a base. And if we look on our Appendix D and we find ammonia, the Kb is 1.8 times 10 to the negative 5. So down here, I'm going to write Kb 1.8 times 10 to the negative 5. I need the Ka. So let's let our calculator do the work. We can find the Ka by doing the constant, the Kw, right, for water is 1 times 10 to the negative 14th divided by Kb will give me my Ka. So the log of, if I do this divided by that, I get Ka. So now let's do plus the log of our base, which is our 0.118, divided by my acid, 0.150. And let's see what we get here. The negative log of 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5. We're going to plus the log of 0.118 divided by 0.150. We get a pH of 9.15. And if we think of this, does this make sense? Well, that's a basic pH, and we have our NH3, our ammonia. So yeah, we will have a basic pH. This next one says, write the net ionic equation for the reaction that occurs when a few drops of nitric acid are added to the buffer. So let's think about what our buffer is. Our buffer, right up here, is made up of NH3, which is our base, and NH4 plus, which is our conjugate acid. All right, so this is our buffer solution. So we're adding nitric acid, which is HNO3. So acid is going to react with the base, NH3. Now, we can leave off this nitrate because that's just going to be a spectator ion. And we can just look at the H plus from that acid reacting with our base. So we have this proton donor going to come over here and it's going to create an H4 more acid, the conjugate acid. Remember, if we went back and looked at our diagram from the last notes, we have our buffered system. We're adding a strong acid. So we have our H plus the conjugate base to give us more acid. That's it. The next says, write a complete ionic equation for the reaction that occurs when a few drops of potassium hydroxide are added to the buffer. So if we look at KOH, we know the potassium hydroxide, specifically this OH, this is a strong base. So the potassium, we can leave that off because that's just going to be a spectator ion. We'll cross that off just like we did over here. So we're going to be left with OH minus. OH minus, our base, will react with the conjugate acid from our buffer. So not the NH3, the NH3 base wants to react with the acid, if that's added. The NH4 reacting with, so the base wants to react with the acid. Again, our acid is our proton donor, so it's going, one of our H's will go over here, so we're going to have water, and then we're left with NH3. So we can see that when a base, strong base, is added to the buffer, it's going to react with the conjugate acid to form water and more of the base. And again, if we go back to my diagram, here we have our buffered solution. We're going to add a strong base. So we have hydroxide plus the acid to give us water and more of the conjugate base. This next one says, how many grams of sodium lactate? Well, first thing that, when I think of grams, I think of moles, right? And when we're doing all of our concentration equations here, we know that we can get to moles if we know molarity. So it's asking us grams of sodium lactate. Now remember, sodium lactate, that's our salt, and our salt 100% dissociates into that conjugate base. So this is asking for that anion, that base. Should be added to 1 liter of 0.15 molar lactic acid, so we know our concentration of our acid, to form a buffer solution with a pH of 4. Assume that no volume changes. Okay, so we know the Henderson-Hasselbach pH is equal to pKa plus a log of B over A. All right, so let's plug in what we know. We know the pH is 4.00 is equal to the negative log of, let's look up lactic acid. We actually did that way up in the problem up there. It's Ka is 1.4 times 10 to the negative fourth plus the log. We don't know what the base is, but we do know the acid is 0.15 molar. Okay, let's do a little bit of simplifying. If I do the negative log of 1.4 times 10 to the negative fourth, I get 3.85. So before I even move on to over here, I want to subtract this from both sides to do a little bit of reduction. So let's subtract 3.85 from both sides. So 4 minus my answer. So I could reduce this right off the bat and get 0.146 is equal to the log of base over 0.15. Now to get rid of log we need to, the opposite of log is 10 to the power of 0.146 will then be equal to base over 0.15. So let's plug that in, 10 to the power of, my answer, we get 1.4. So we can then say 1.4 is equal to base over 0.15. So now we just need to multiply these two together to get B. So B is equal to 1.4 times 0.15. We get 0.21 molar. Now remember, that is moles per liter. All right, so we still got a little bit of work left to do. This 0.21 molar, I'm going to go over here. 0.21 is moles per liter. And we were told that it's in 1 liter, so 0.21 times 1 still gives us 0.21 moles of sodium lactate, which is NaC3H5O3. Now, to get rid of moles and get to grams, we need to find the molar mass. So 1 mole will be on the bottom here. And let's add up our molar mass. We've got sodium, which is 23, plus carbon of 12 times 3, plus 5 hydrogens, plus 16 times 3 for our oxygens, and I got 112 grams per mole. So 0.21 times 112, and I should get 23.52 grams. And let's just make sure we've got 3 sig figs, 2 sig figs it looks like. So we're going to say 24 grams of this sodium lactate. Question number 5 says we have a buffer solution that contains 0.12 moles of our propionic acid. So here's our acid. We're given moles. We're also told that it's in 1.5 liters. So let's figure out the concentration of our acid. So 0.12 moles divided by 1.5 liters will give us 0.12 divided by 1.5 liters, 0.08 molar. So our acid 0.08 molar solution. Then we have 0.1 moles of our sodium propionate, which is our base. So this is our acid, and then we have our base. We need to do our moles divided by 1.5 liters. So let's do that next. 0.1 divided by 1.5. So we get 0.067. Let's do that. 0.067 molar for our base. Okay? So what is the pH of this buffer? Well, we know that pH is equal to the negative, well, pKa, we'll just keep doing that, plus the log of base over acid. So pH is equal to the negative log of our Ka. So we need to look up propionic acid here real quick. And propionic acid is 1.3 times 10 to the negative 5 plus the log of our base, we said was 0.067, and our acid we found was 0.08. So let's do some calculator plugging. Negative log of 1.3 times 10 to the negative 5 plus the log of 0.067 divided by 0.08. We should get 4.81 pH. That's an acidic solution, and we started off with our acid, so that makes sense. Now let's look the pH of the buffer after we add 0.1 mole of sodium hydroxide. Well, since we're given moles here, let's write out what's happening. We've got our NaOH, so we have hydroxide. We're going to drop the Na because that's just a spectator. So we have base, and it's going to be reacting with our acid, our propionic acid. I'm just going to say HA for our acid symbolizing. And we know that our acid is going to be a proton donor. We're going to have water, and what's going to be left over? Our conjugate base. All right, so let's write down what we started with before. And let's just look at moles. We'll change it to concentration here in just a minute, but since we're given moles here, let's look at this. So before, we are given, let's see, 0.01 hydroxide. Before, how much acid did I have? 0.12 moles of acid. All right, and I also had 0.1 moles of my conjugate base, 0.1. Now let's look at what's going to get used up here. Definitely the smaller one will get used up first. So we're going to subtract 0.01, subtract 0.01, add 0.01. So not going to be any of that left. So this is after. So 0.12 minus 0.01 would be 0.11 moles. Over here I have 0.1 plus 0.01, so I'm going to have 0.11 moles. Now I can look at concentration. I can look at my acid and my conjugate base concentration by taking those moles, dividing it by 1.5 liters. Okay, so let's find those concentrations now. All right, so 0.11 divided by 1.5 gives me a concentration of 0.073. I'm going to write that here. And it's the same concentration for both of these, 0.073 0.11 divided by 1.5, so both of these will have the same concentration. So I'm just going to write it once since I don't have very much room. All right, so now let's write out our Henderson-Hasselbach equation. We've got pH is equal to the negative log, same propionic acid, the 1.3 times 10 to the negative 5, plus the log of our base over our acid, and these are both the same numbers, 0.073 over 0.073. All right, let's see what we get. Negative log of 1.3 times 10 to the negative 5 plus the log 0.073 divided by 0.073. Notice 0.073 divided by 0.073 would give us the answer of 1, right? And so we get the same as just the negative log of that. So our pH should be 4.89. And notice that we added hydroxide, we added a base, and we went from 4.81 to 4.89. So our number did increase, making it more basic, very slightly more basic. This next one, letter C, what's the pH of the buffer after we add 0.01 moles of hydroiodic acid? So we're going to do the same thing here, except for instead of adding a base, we're adding acid. So I'm going to write out that we have our H plus, I'm leaving off the iodine because that's just a spectator. But if I'm adding acid, it's going to be reacting with the conjugate base, right? So I'm just going to write A minus. We don't need to write the whole propriate. So we have H plus A, and we're going to make more acid, right? It's going to create our propionic acid. So what did we start with? We're going to write before here. It told us that we have 0.01 moles of our acid. How much base did we start with? Way up here it told us we started with propionic, 0.1 moles of it. And how much acid did we start with? 0.12. Again, we're just looking at moles, just because they're telling me that they're giving us in moles. Now, which one's going to get used up first? The smaller one. So we're going to subtract 0.01. So after, we're going to have none of that left, minus 0.01, and then we're going to plus 0.01. So 1.1 minus 0.01, we should get 0.09 moles, right? This is all in moles. And now to get that concentration, we do need to divide it by, it was in 1.5 liters. So this will give us 0.13, and that's moles divided by 1.5 liters. All right, let's find our concentrations here. Then we can plug it into our Henderson-Hasselbach. 0.09 divided by 1.5, so 0.06. I'm going to write that in right here. 0.06 molar, that's for my conjugate base, and 0.13 divided by 1.5, 0.087, let's write that, 0.087 for my acid. All right, now let's plug it into our pH is equal to the negative log of our Ka, which is the 1.3 times 10 to the negative 5, plus the log of my base, we said was 0.06, over my acid, which we said was 0.087. Negative log of 1.3 times 10 to the negative 5 plus the log of 0.06 divided by 0.087. We got a pH of 4.72, almost 0.73, but 4.72. If we look at that, Let's compare this value. So up here, our first time when we just looked at the buffer, we had a 4.81. When we added base, notice it went up 4.89, so it became more basic. If I compare my buffer, and here I added acid, it went down 4.72, which to become more acidic, it lowers the pH. So all of these make sense. All right, last practice problem. All right, this one, I noticed that it was missing a very relevant piece of information. So we have to prepare a buffer with a pH of 4.80. You have the following 0.1 molar solutions available: formic acid and sodium formate. So that's our first option. Formic acid would be my acid. The conjugate base would be the sodium formate. Number 2, we have propionic acid with sodium propionate. P-R-O-P. There we go. And number 3, phosphoric acid and sodium dihydrogen phosphate. So sodium, phosphoric, and sodium. So all of these are acids with their conjugate bases. Okay, so here are 3 different buffer solutions. We have 0.1 molar solutions of all of these. Which one should we use? Well, think about what we know. pH is equal to pKa plus the log of base over acid. And we know that when the ideal situation is that the pH is equal to the pKa. And we had an example up above where we had equal amounts of concentration of the base and the acid, which made the pH equal to the pKa. Remember when we did the negative log of 1.3 times 10 to the negative 5? We got 4.89, which is equal to, if we added the log of both of those being the same concentrations, that just became nothing. So ideal situation is when pH is equal to pKa. So we would love for the base and the acid to have the same concentration to make this happen. So let's see what these Ka values are to see what's the closest to the pH of 4.8. So I need to look up on our Appendix D formic acid, and formic acid is 1.8 times 10 to the negative 4. That's our Ka. So our pKa, the negative log of 1.8 times 10 to the negative 4 is 3.74. Let's look up propionic acid. On my appendix, propionic acid, we just used that up above, didn't we? So the Ka is 1.3 times 10 to the negative 5th. And we just did that math. 1.3 times to the negative 5th was 4.89. And let's look up phosphoric acid. Phosphoric acid, we'll use the K1 value, 7.5 times 10 to the negative 3. So the pKa would be negative log of 7.5 times 10 to the negative 3. We get 2.12. So we want a pH value of 4.80. Which one of these is closest? with plus or minus within a pH point value, and it would definitely be our propionic acid. So this is the solution we would want to prepare a buffer with about a 4.80 pH, where our pH is equal to pKa. And last, how many milliliters of each solution would you use to make a liter of this buffer? Well, remember, we want equal concentration of our base and our acid. Remember, concentration is moles per liter. So if we have the same number of moles of each of these, which I'm assuming that we do, because we have 0.1 molar solutions, so the same concentration. So we would just want 500 milliliters of each, 500 milliliters of our acid and 500 milliliters of our base to give us 1,000 milliliters or 1 liter total. Because again, if we have the same concentration, then we take that part of the equation out and we have our pKa equal to the pH.